In this lesson, we're going to define what rational functions are and some of their characteristics. So we'll start right off with the definition of a rational function. And a rational function has a specific form to it. Rational means a ratio, so a rational function is basically comprised of the ratio of two polynomial functions, so p of x over q of x. So that means p of x and q of x are polynomials. And then we also have to understand that q of x can't be equal to 0. So some characteristics of rational functions. If we have our x and y axis, rational functions will have a vertical asymptote, because if I have a polynomial, any kind of polynomial in the denominator, there will be a spot, there will be a value of the variable that will make the denominator 0. So that's going to create a vertical asymptote. Now sometimes it'll be a vertical asymptote. We have something called a slant asymptote or even a hole, but all of those are a discontinuity because of the fact that we have a polynomial in the denominator. These functions will also have a horizontal asymptote. So just as an example, I might have a vertical asymptote on the y-axis and a horizontal asymptote on the x-axis. A vertical asymptote means that the function isn't going to cross it, but a rational function may cross a horizontal asymptote, just not at the ends as it approaches positive or negative infinity. But in the middle of the function, it may cross the horizontal asymptote. It will never cross the vertical asymptote, though. So now we're going to look more specifically at the vertical and horizontal asymptotes. So let's define what a vertical asymptote is. A rational function may have more than one vertical asymptote, but it has to do with the x values. So it's an x equals equation. And it's basically where the rational function is undefined. And more specifically, it would be where the domain is undefined, where we cannot substitute in a value for x and come up with an answer. So basically, as my x values approaches a vertical asymptote, my y values are going to approach positive or negative infinity. So vertical asymptote, my y values are going to approach either positive infinity or negative infinity. Okay, so an example, if I have a vertical asymptote here, my function might do something like that, where it won't cross. Sometimes they go in the same direction, so if I have a vertical asymptote, it could be that my rational function might do something like this. Either way, they cannot cross it. So if we want to find the vertical asymptotes, it's basically undefined when my rational function is undefined, and we know that happens when we have a 0 in the denominator. So basically what you have to do is set the denominator equal to 0 and solve. You're basically trying to define the domain like we used to do in the beginning of the year. Set the denominator equal to 0 and solve. So we'll work through an example or two, and then we'll look at horizontal asymptotes. Alright, so here's our example. We have a rational function. It's a ratio of two polynomials, 3x squared plus 6x over x squared minus 2x minus 3. And what we want to do is find the vertical asymptotes. Well, what I would do first is I would factor the numerator and the denominator just to see if there's any common factors. And if there are no common factors, then we're going to set each factor in the denominator equal to 0. So if we factor that thing, r of x, in the numerator, there's a GCF, 3x times x plus 2. And then in the denominator, we have x minus 3 and x plus 1. So if you see, there's nothing in common between the factors in the numerator and the factors in the denominator. So because of that, we know we're going to have the factors of the denominator are going to create two vertical asymptotes. We have one at x minus, or when x minus 3 is equal to 0, and when x plus 1 is equal to 0. So I'm going to have a vertical asymptote at x is equal to 3, and x is equal to negative 1. So in class, we'll put this in our calculator and we'll take a look to see what that thing looks like as far as vertical asymptotes. But now let's talk about the horizontal asymptotes. The horizontal asymptote is the behavior of the function as x approaches positive or negative infinity. It's like the end behavior. For polynomial functions, we don't have a horizontal asymptote, but for rational functions, we do. The values approach a specific value as x approaches positive or negative infinity. So we can look at this in two ways. There's two ways to do this. The first one is numerically. So basically, if we are trying to figure out what happens as x approaches positive or negative infinity, we can get a good idea by evaluating r of x for very large values of x, like 100 or 1,000 or 10,000. You will start to see that the values would converge on a specific number. So if we use the example that we found for the vertical asymptotes, and I want to figure out where the horizontal asymptote would show up, I'm basically going to take this and I'm going to evaluate it for r of, let's say, 10,000. And you would substitute that in. That would be 3 times 10,000 squared plus 6 times 10,000 all over 10,000 squared minus 2 times 10,000 minus 3. It's a little tedious, but that's what you would do. Now if you look at that and just think about it, 10,000 squared is 10,000 times as large as as the 10,000 not squared. And you have the same thing on the bottom. So what's going to happen is that all of this stuff is going to be relatively small compared to the 3 times 10,000 squared divided by 10,000 squared. So we're really just looking at this guy. And when you take 3 times a big number and divide it by that big number, this is going to reduce down to just 3. Your calculator will show you that. If you substitute all of this in, you're going to come up with a value that r of 10,000 is going to be equal to 3. So my horizontal asymptote is a y equals equation, and it's going to be y is equal to 3. Now instead of doing this numerically, there is another way to do this intuitively. And you're basically going to look at the ratio of the leading terms. So if my rational function has a polynomial, is a ratio, it always is, so my rational function is a ratio of two polynomials, I want the highest degree term in the numerator over the highest degree term in the denominator. And we're going to look at the degree of the numerator and the denominator, and there are 3 cases here. The first case is if the degree of p of x is equal to the degree of q of x. So if they have the same degree, what that means is for very large values of x, everything's going to divide away except the leading coefficient. So in the end, your horizontal asymptote is going to look something like this. It's going to be the leading coefficient of the numerator, so the coefficient of the highest degree term, divided by the leading coefficient of the denominator, the coefficient of the highest degree term in the denominator. That's if the degrees are the same, because everything else divides away. The second case is if the denominator has a higher degree than the numerator. That means the value in the denominator is going to get larger and larger and larger, which means you have a situation where you have like 1 over 1,000 or 1 over 1,000,000. Well, a fraction whose denominator is much greater than the numerator basically approaches a value of 0. So in that case, if the degree of the denominator is greater than the degree of the numerator, my horizontal asymptote is going to be the x-axis. Y is equal to 0. Finally, if the degree of the numerator is greater than the degree of the denominator, we don't have a horizontal asymptote, and the function just keeps increasing. So there's no horizontal asymptote in that case. We might have something called a slant asymptote, which we may get into if we have some extra time. And that's where the degree is only 1 degree higher in the numerator than the denominator. And then the asymptote kind of is aligned with a specific slope, but it's not horizontal. So the horizontal asymptote doesn't exist if the degree of the numerator is greater than the denominator. Alright, so I'll demonstrate all of this with an example, and then we're going to graph this example in class. If you have your graphing calculator with you, then I'd encourage you to graph it on there as well. So we're going to find the vertical and horizontal asymptotes of this function. R of x is 2x plus 3 over x squared minus 49. For the vertical asymptote, we basically set the denominator equal to 0 and solve it. It's a second degree, which means I'm going to have 2 factors. That's a difference of squares, x plus 7, x minus 7, so that means in the end x is going to be equal to negative 7, and x is going to be equal to positive 7. These are x equals equations. They are vertical lines, so you got to show them that way. X is equal to negative 7 and x is equal to 7. For the horizontal asymptote, if you look at the ratio, the degree of the numerator is first degree. The degree of the denominator is a second degree. So the degree of the denominator is greater than the numerator. That means as x approaches large positive or negative values, the denominator is going to take over, and the entire function is going to approach 0. So y is equal to 0. That's my horizontal asymptote. Again, we'll look at the graphs in class, and we will practice more of this in class.